It was not an internal exercise or a routine simulation filed away without practical consequences. When the new orbital calculations appeared in NASA systems, the change was significant enough to activate formal planetary defense protocols. Asteroid 2024 YR4 had been monitored since its discovery in 2024, initially classified as just another near-Earth object within the vast catalogue of bodies tracked by international observatories. During the first months, its orbit appeared relatively predictable, although it crossed Earth's trajectory, a typical characteristic of Apollo group asteroids that require constant monitoring due to their potential for close approaches. In 2025, preliminary analyses indicated a 3.1% probability of collision with Earth during a future orbital passage, a figure statistically sufficient to mobilize monitoring centers across multiple continents, although the percentage seemed small to the general public. In orbital mathematics, any value above zero demands rigorous attention, especially when it involves objects tens of meters wide, traveling at extreme velocities. With an estimated diameter between 53 and 67 meters, 202 for YR4 is comparable in size to a 10-story building, large enough to cause significant regional damage in the event of a direct impact. The energy released by an object of this magnitude could exceed multiple conventional explosions combined, depending on entry angle, relative velocity, and structural composition. Faced with this early scenario, high-resolution optical telescopes and planetary radar systems intensified their measurements to reduce mathematical uncertainties associated with its predicted orbit. It was during this continuous refinement process that the decisive shift in calculations occurred. New data collected by precision ground-based telescopes and the James Webb Space Telescope allowed gravitational models to be updated with greater statistical detail. With these additional measurements, the risk of impact with Earth was officially ruled out, eliminating the possibility of direct collision in 2032, according to the latest projections. However, the elimination of terrestrial risk revealed another orbital scenario equally relevant from scientific and strategic perspectives. New simulations indicated a 4.3% probability of impact with the Moon on December 22, 2032. The European Space Agency presented a very similar estimate, calculating approximately a 4% chance of lunar collision on the same date. Although the Moon is uninhabited, the shift in projected target was sufficient to activate intensified surveillance protocols. The potential impact point was projected near the Tycho crater, located in the southern hemisphere of the lunar surface. The estimated time of the event was calculated at approximately 12 EJO Brasilia time. Considering current orbital uncertainty margins, even relatively modest probabilities are treated seriously when involving objects monitored by major space agencies. Planetary defense systems operate based on prevention and early analysis, not solely in response to immediate threats. The central objective is to understand every orbital variable with increasing mathematical precision over time. Small gravitational forces accumulated over years can significantly alter trajectories, initially predicted with confidence. Subtle interactions with the gravity of Earth, the Moon, and other planetary bodies must be continuously recalculated. Each new observation reduces the margin of error associated with the asteroid's future position. If a lunar impact is confirmed, the event may be visible from Earth as a temporary flash in the night sky. Estimates suggest the collision could create a crater approximately 1 kilometer wide on the lunar surface. The projected depth of the crater could reach around 150 meters. Depending on the geological composition of the impacted region, the energy released would be comparable to a major natural explosion. Though without any direct consequences for Earth, the brief flash could reach brightness similar to that of the planet Venus under optimal viewing conditions. Regions in East Asia, Oceania, Hawaii, and the west coast of North America would have the best viewing opportunities. Beyond the visual spectacle, the impact would generate seismic waves detectable by instruments installed on the lunar surface. Previous missions left sensors capable of recording vibrations resulting from natural collisions and internal activity. Such records would provide valuable data about the internal structure of the Moon and its response to energetic impacts. The study of ejected material would also allow investigation of the asteroid's internal composition. Fragments launched into space could be analyzed by high-sensitivity telescopes for weeks following the event. Even without risk to Earth, The event represents an exceptionally rare scientific opportunity. The absence of atmosphere on the Moon allows impacts to be observed directly and in detail. On Earth, atmospheric and erosive processes quickly alter evidence of recent collisions. On the lunar surface, impact marks remain preserved for millions or even billions of years. Continuous monitoring of 2024 YR4 involves systems such as Pan-STARRS and Catalina Sky Survey. These programs conduct systematic sky surveys, searching for potentially hazardous objects. Advanced algorithms processed large volumes of data in real time, identifying relevant orbital patterns. Any unexpected deviation from the predicted trajectory is immediately flagged for specialized review. Modern planetary defense is built upon constant international cooperation and transparent information exchange. NASA and ESA share critical data to ensure consistent and coordinated predictions. The DART mission recently demonstrated that it is possible to alter an asteroid's trajectory through controlled impact. Although no intervention is required in this specific case, the technology has been experimentally validated. The case of 2024 YR4 reinforces the importance of early warning systems and continuous surveillance. Decades ago, a similar object might have been detected only months before a significant approach. Today, computational models simulate millions of alternative orbital scenarios with remarkable precision. Each simulation considers small variations in velocity, position, and accumulated gravitational influence. The objective is to map all statistical possibilities leading up to the year 2032. The greater the temporal distance from the predicted event, the larger the associated uncertainty margin. For this reason, observations will continue to be refined over the coming years. High-power planetary radars may be used during future approaches of the asteroid. These instruments allow distance and velocity measurements far more precise than optical observation alone. Although uninhabited, the Moon has become a strategic focus of international scientific exploration. Natural impacts provide important data for planning future lunar bases. Understanding the frequency and intensity of such events is essential for long-term crewed missions. Asteroid 2024 YR4 has shifted from potential terrestrial threat to natural scientific laboratory. This transition demonstrates how science constantly evolves as new information is incorporated. It is not a matter of alarmism, but of technical monitoring based on verifiable data. The universe is a dynamic environment filled with remnants from the formation of the solar system. Asteroids cross planetary orbits more frequently than most people imagine. The vast majority never approach Earth or the Moon in a dangerous way. Some, however, require detailed monitoring due to complex orbital intersections. This is one of those specific cases. If a lunar impact occurs, it will become one of the most studied astronomical events of the decade. If it does not occur, it will represent another confirmation of the growing precision of modern orbital models. In both scenarios, science advances significantly. The activation of protocols reflects institutional maturity in the field of planetary defense. Planetary defense does not belong to science fiction, but to applied mathematics and physics. It is a discipline grounded in orbital mechanics, statistics, and continuous global cooperation. As 2032 gradually approaches on the calendar, telescopes remain vigilant night after night. Each new measurement contributes to reducing residual uncertainties. Each new dataset improves future predictions. The story of 2024 YR4 illustrates humanity's ability to anticipate cosmic events years in advance. We live in an active solar system where rocky bodies follow complex and dynamic trajectories. Monitoring them is an essential part of modern technological evolution. Because understanding space also means protecting our collective future. And following these events reminds us that we are part of a larger and constantly changing universe. If you want to continue exploring real stories about planetary defense, astronomy, and the challenges of the cosmos, subscribe to the channel and stay connected, because the next calculation may reveal even more about our place in the universe.